Welcome to Chapter 1, Section 9, Inverse Functions. In this section, we're going to look at functions and their inverses and the properties that inverse functions have. And so to start, let's look at a function f of x equals x plus 3. And if we wanted to graph this, we could simply just graph the linear relationship, or we could look at a table of x, y values, independent and dependent variables. So let's just pick some dependent values of, let's say, -1, 0, 1, 2. Okay, so when we plug this in, -1 is x, and so y is going to equal 2, and then when we put in 0, we get 3 and 4 and 5. All right, well, that's a set of data for this function f of x equals x plus 3. Well, the inverse, and the definition of an inverse is when we switch x and y values. So the x and y values switch, so our new function would have x values of 2, 3, 4, and 5, and then our y values would now be -1, 0, 1, 2. Okay, that's the definition of an inverse. Going from here to here, that gives us an inverse function. Now, what does the inverse function look like? Well, this is actually f of x equals x minus 3. Notice, inverse operation on x. We're adding 3 over in this one, and this function, the inverse, is x minus 3. Now, we denote inverses by having an exponent of -1 in our f. So we call this, we don't actually say f to the -1 of x, we say inverse of f of x is x minus 3. Okay, and we can even confirm 2 minus 3 is -1, 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2. Now, what we're going to do is we're going to look at both graphically and analytically how to find inverses and how to determine if functions are inverses of one another. So first, let's have a formal definition of what an inverse function is. So let's say we have a function g of x and a function f of x. And these two functions are inverses if and only if, and so IFF stands for if and only if, g of f of x equals x and f of g of x equals x. And this is for all x's in the domain. All right, so this is it's a property and a definition of what inverse functions are. This tells us a way that we can test to see if two functions are inverses of each other, and it also lets us know what to expect of an inverse function. And remember, this is the composite. It's when we plug f into g and we get out x, and if we plug g into f, we get out x, then we know that the two functions are inverses of each other. So let's look at the examples that we had just a moment ago of a function f of x equals x plus 3, and let's call the other function g of x x minus 3. Well, let's look at f of g of x, and that is taking this x minus 3 and plugging it in x's place. So that's the quantity x minus 3 plus 3. And what do we get from that? We get x. Okay, well, that meets one of the requirements, but in order to be an inverse, it has to meet the requirement of g of f of x. So we want to plug this into the x value here, so we get x plus 3, that quantity, minus 3, and that gives us x. So that confirms, by the definition, these two functions are in fact inverses of each other. Another example of inverse functions would be the function f of x equal to the square root of x, and the inverse of that, g of x, would be x squared. Now, one thing we have to keep in mind here, that inverses are constrained by the domain of their original function, and we're going to get into that a little further in a moment. But let's just look at these two functions and let's confirm that they are inverses first. So f of g of x would mean that we would have to plug in g into f, so that would be x squared inside of a radical, which does in fact give us x. And then if we look once again at g of f of x, we take the square root of x and we want to square that, and that also gives us x. So we can say that f and g are inverses of each other. Well, let's actually take a look at the graph of these two. And if we look at right here, the red is our function g, which is the square root of x. And if we look at its inverse, x squared, we see that these two graphs are symmetrical, but they're not symmetrical about the origin or symmetrical about the axis. They're actually symmetrical about this dotted line right here, which is significant. That dotted line is the line of y equals x. And so that actually happens for all inverses. All inverses are symmetrical about y equals x. They have some symmetry about this right here, y equals x. And this is going to happen for all inverse functions. Okay? Now, let's talk about the domain a little bit here. Well, what is the domain of f? Well, our domain here is only 0 to infinity. All right, we can include 0, but we can't have anything that's negative. So that means that if we say g is an inverse, g is actually only an inverse on the interval such that x is also defined from 0 to infinity. So this constrains our inverse a little bit, okay? So, and if we look at the graph, that confirms that really it's only symmetrical for this portion of the parabola here, this portion of the blue curve. And so, and that's only the portion where x is from 0 to infinity. Okay, so now we haven't gotten to the point where we're finding inverses yet, and we will get to that. But let's talk about different types of functions that either can or can't have inverses. Not all functions can have an inverse function. And in order for a function to have an inverse, it must pass the horizontal line test. And in order to pass the horizontal line test, that means that a horizontal line cannot pass the graph more than once. All right, so for every input, there has to be exactly only one output. And that also means that we can't have two different inputs that lead to the same output. There has to be something called a one-to-one relationship. Okay, so for example, if we look at the graph of just a basic parabola here, all right, notice that this passes the vertical line test, so it is a function, but it does not pass a horizontal line test because a horizontal line will cross at two different points. So this does not have an inverse. All right, and you might ask, well, wait a minute, we just saw that x squared had an inverse. Yes, x squared on a limited domain will have an inverse, but the entire graph of x squared does not. All right, another example is if we looked at a cubic, and so let's just look at a cubic graph here. Looks something like that. Notice that this would pass any horizontal line we would draw, and so since it passes the horizontal line test, it does have an inverse, and its inverse is also a function. Okay, well, let's take a look and see how do we actually find an inverse. And so there's a process that we're going to go through to given a function to try to find the inverse of that function. First, we have to check the horizontal line test. So for step one will be check the horizontal line test to see, is this even a function? Is the inverse a function? Does it exist? And so if it passes, then we're going to take the equation and we're going to switch x and y. All right, so let's look at an example here. Let's say we have f of x is equal to, and let's just have a simple one, 2x minus 1. Okay, you know what, let's have 2x minus 4. We'll make it easier on us, and you'll see why in a second. Well, we know we can express this as y equals 2x minus 4. Okay, so we want to switch the x and the y. So we're going to say, well, instead of y equals 2x minus 4, we'll say that x equals 2y minus 4. And then once you have the switch, go ahead and solve for y. So let's look at this equation, and if we want to solve for y, we need to add 4 to both sides to get x plus 4 equals 2y, and then we want to divide both sides by 2, so we get 1/2 x plus 2 equals y. Well, then this new y we can exchange, so exchange the new y with our inverse function. All right, so we say that this is our inverse. Our inverse of f of x is simply 1/2 x plus 2. And we can confirm that by finding the composite functions. If we plug this function into x's place here, we would get x. And if we plug this function into x's place here, we would get x. And so these two functions are inverses of each other. And notice, we have multiplying by 2, multiplying by 1/2. That's an inverse. We have subtraction, we have addition. So you're going to see basic inverse properties popping up here in our inverse functions. Now you might ask, wait a minute, we're subtracting 4 here, but over here we're adding 2. What's the difference there? Well, that's because of this multiple of 2. This has to reduce by a factor of 2. Okay, so let's take a look at another example here to practice. Let's say we have f of x is equal to the cube root of x plus 1. All right, and we want to know what is the inverse of f. So what is our inverse here? Well, we know our first procedure is, well, let's check the horizontal line test. If you graph this, this is a cube root function. It passes the horizontal line test. It looks kind of like a square root, but it's a little different in that it extends both ways into the positive and negative. And so the domain here, we need to check what's our domain of f. Well, our domain of f is all real numbers. We can go from negative infinity to positive infinity. So this isn't going to constrict our domain of our inverse at all. Okay, so let's do the next step in, let's call this y. And so we have y equals the cube root of the quantity x plus 1. And then let's switch x and y. So we say that x is equal to the cube root of y plus 1. And now we just need to solve for y. Well, in solving for y here, we've got to get rid of the cube root. So we get x cubed is equal to y plus 1. And so then we'll have y equals x cubed minus 1. So this tells us what our inverse is. Our inverse function, our inverse of f is simply x cubed minus 1. Now, if we want to check, well, let's plug in x cubed minus 1 into the cube root of x plus 1. So that would be x cubed minus 1, that quantity plus 1. Take the cube root. Well, negative 1 plus 1, those cancel out. Cube root of x cubed does give us x. So that checks. Well, what if we put the cube root of this quantity into x cubed minus 1? Well, we have the cube root of the quantity x plus 1 cubed minus 1. Well, this gives us x plus 1 minus 1, and that does give us x. Now, what did I do right here? I just looked at the definition of an inverse to double check that what we found is in fact the inverse function. Okay, so you're going to continue to do this in class tomorrow, and you're going to work some problems out of the book. But what I would like you to do first, before you come to class tomorrow, I'd like you to just work a couple problems on page 99. I'd like you to look at 1 through 8. And so try to do these before class tomorrow, and you can come in with any questions. Thank you very much.